In this video here, we're going to take a look at exam revision for proof by induction. So for this video here, all we're going to do is take a look at two exam style questions for proof by induction. So as you can see then, this will cover the following topics. So what do we have here then? Well, we have proving results about sums of series, proving results about divisibility using induction, and then finally here, proving results about matrices using induction. So as always here, what I'd recommend then is that you pause the video, have a go at the questions as they appear, then double check that your solution matches what we get on the screen. So that gives us everything that we need here then to get started. Let's begin now with question 1. So let's get started then on question 1 here for proof by induction. So as always, for any proof by induction question here, we should always start with the base case or the basis step here. So for the basis step here then, let's just underline this here just so we can see each step as we go. All we're going to do here then is let n equal 1. So we let n equal 1 here. Now, if n equals 1 then, what I want to do here is show that the left-hand side is equal to the right-hand side here. So for the left-hand side then, which we'll just shorten or abbreviate to LHS here, what we get then is the summation here from r equals 1 to 1 of r times r plus 3. As we said, then we get the summation here from r equals 1 to 1 of r times r plus 3. So r times r plus 3 here, which in this case then will give us 1 times 1 plus 3. So we get 1 times by 4 there, and we get 4. So basically all we need to do now is show that the right-hand side is also equal to 4. So for the right-hand side here then, what do we get? Again, if n equals 1 here, what we get then is 1 over 3 times 1. That's going to be 1 over 3. We then times this here by this first bracket of 1 plus 1, so that's going to be 2. And then we times this here by the second bracket of n plus 5. So if n equals 1, we get 1 plus 5, which is 6 there. Okay. Well, 2 times 6 is 12. Divide that by 3, and again, we get 4 here. Perfect. So what that means then is this result here holds for n equals 1. So therefore, we can say that it's true for n equals 1. Okay. So that's the basis step complete. We now move on to the assumption step here. So for the assumption step then, what we say now then, okay, let me just highlight this here, just to make it clear, is we assume that this result here is true for n equals k. So assume true then. So assume true for n equals k. Okay. Now if we assume that this is true for n equals k, what do we get then? Well, I get the summation here from r equals 1 to k then of r times r plus 3. So r times r plus 3 here. And if we assume that it's true for n equals k, what we get then is 1 over 3 times k plus 1 times k plus 5 then. So let me just write all of that down here. So 1 over 3k times k plus 1 times k plus 5 here. Okay. Now for the next step then, this is the most important step here, and this is really where the magic happens then for proof by induction. The next step then is the inductive step here. So for the inductive step here then, what do we do? Again, let me just underline this here just to make it clear. So for the inductive step here then, what we do is we let n equal k plus 1. We let n equal k plus 1 here. Now, if n equals k plus 1 here then, what we get here is the summation from r equals 1 to k plus 1 of r times r plus 3. So r times r plus 3. So before we take a look at what this is actually equal to then, just take a moment here to think about how this summation then relates to the previous step here, or our assumption step then, and how we can use this then to help us with the inductive step. And hopefully you can see then that this here then will be equal to the summation from r equals 1 to k of r times r plus 3. So basically what that gives us then is the result here from the previous step, which we know is true for n equals k, or we assumed is true anyway for n equals k. And then we have the very last term here in this summation. So in that case then, we add on k plus 1. So k plus 1 times by k plus 4 there. Okay. Like so. So that's the very last term here in the summation. Okay. So this part here then, well, in the previous part, we assumed it's true for n equals k. So we know this part here is true anyway for n equals k. So we can now replace this here with the previous result then that we had in the previous step anyway. So we get 1 over 3. So 1 over 3 k here times by k plus 1 times by k plus 5. Like so. We then also have the k plus 1 and the k plus 4 here. So plus k plus 1 and k plus 4. So what can we do next here then? Well, I can factor out a 1 over 3 k plus 1 here. Okay, so if we factor out a 1 over 3 k plus 1, so 1 over 3 k plus 1 here, we factor that out like so. So what do we get left over with here then? So once we factor out the 1 over 3 k plus 1 here, well, in that case then, I get k times k plus 5. So k times k plus 5. We then also have, well, this part here then, I must times it by 3 because we factored out the 1 over 3 here, so I get 3 lots of k plus 4. So 3 lots of k plus 4 here. Like so. Now, for this part here then, well, we can simplify everything inside the square brackets here. K times k would give me k squared. K times 5 is 5k. Expand this bracket here as well. 3 times k is 3k. 3 times 4 is 12. So once we simplify all of this here then, what I get is 1 over 3 times k plus 1. We then have this part here is simplified. So once I simplify this then, what I get here is k squared. I get k squared plus 8k plus 12. So plus 8k plus 12. Now what I want to do here then is factorize this part, right? So altogether then what I've got here is 1 over 3 times k plus 1. And we can now factorize this quadratic here then. So once we factorize this quadratic here, what I get then is k plus 2 and k plus 6 here. Okay, like so. And we're pretty much done now. All we need to do here is show whether k plus 1 can be substituted in. So if we do that then, I'll do it over here just to show how we finish our solution then. So I get 1 over 3 here. So 1 over 3 times k plus 1. So that's fine. 1 over 3 times k plus 1. Then for this second bracket here, we can write this as k plus 1 plus 1. So I get k plus 1 plus 1, like so. And then for the third bracket here, then we get k plus 1 plus 5 there. Okay, so let me put that in a bracket here. K plus 1 plus 5 there. Okay, and there we have it. So that brings us pretty much to the end then of this question here. The only thing left to do now is give the conclusion here. So I've run out of room, as you can see here. So all I'm going to do then is quickly clear the screen and I will give the conclusion here. So to finish question 1 off then, as we've mentioned here, we've cleared the screen. And what I've given you here then is the conclusion to our proof by induction. So this is important. We should always give a conclusion here to a proof by induction question. It is always the worst part of a question here, but it is important. So what do we say then? Well, as you can see then, if the result is true for n equals k, then it is shown to be true for n equals k plus 1. And as the result is true for n equals 1, it is also true for all n that belongs to the set of positive integers by induction. So just in case you're not familiar with this notation here, this funny looking z with a little plus above it here, this is the set of positive integers. Okay, so there we have it. Like I said, it is important that you give the conclusion here to a proof by induction. Please do not miss out this step here. You will lose marks. Okay, so there we have it. So that gives us the solution there to question 1. So let's just take a look then at one more question here. So for question 2 then, all we're looking at doing here is proving matrix results using induction. So as always, for any proof by induction question here, we start with the basis step or the base case here, whichever you prefer to call it. So for the basis step here then, I'm just going to start by letting n equal 1 here. So let n equal 1. Okay. So what do we get then on the left-hand side here? So for the left-hand side then, what I get here is this matrix here to the power of 1. I get 3 minus 4, 1, minus 1 here, power of 1, which is simply equal then, I get 3 minus 4, 1, and minus 1 there. Okay. So that's the left-hand side of our equation here. Now for the right-hand side here then, what do we get? So for the right-hand side then, well, I get 2 lots of 1 plus 1. Let me write this down in full. So I get 2 lots of 1 plus 1. I then get minus 4 lots of 1. Minus 4 lots of 1 here. I then get 1 in the bottom left corner. And then finally here, I get minus 2 lots of 1 plus 1. Minus 2 lots of 1 plus 1 there. Okay. I'm going to room a little bit there, but just about fitting it on. So if we simplify this matrix here, then what do we get? Well, we get 2 lots of 1 plus 1, so that's 3. Minus 4 lots of 1 is minus 4. 1. And then finally here, minus 2 lots of 1 plus 1 gives us minus 1 there. Okay. In that case, then we get the same here on the left-hand side and the right-hand side. So therefore, this is true then. Therefore, true for n equals 1 here. Okay. So that's the basis step complete there. So we now move on to the assumption step here then. So for the assumption step here, what we do now is we assume that this is true for n equals k here. So assume true for n equals k. Okay. So if this is true then for n equals k, what do we have here? Well, I've got this matrix then to the power of k. So I've got 3 minus 4, 1, and minus 1 to the power of k here. And that is equal then. So I get 2 lots of k plus 1. So 2k plus 1. I then get minus 4k here. I then got k here in the bottom left corner. And then finally we get minus 2k plus 1 here. Okay. So that's the assumption step complete here. Let me just underline this here just to show that it's one of our steps. So now what we move on to here is the inductive step, the magic part of any proof by induction question. So for the inductive step then, let's just write this down. So for the inductive step here, what do we have then? Well, what we do now is we let n equal k plus 1 here. So let n equal k plus 1. So if n equals k plus 1 here then, what we have now is this matrix here to the power of k plus 1. I get 3 minus 4, 1, and minus 1 to the power then of k plus 1. Like so. Now this matrix here then, What I want to do then is use the previous result here that we assumed is true for n equals k. So to do that, we need to write this as a product here then of two matrices, or product of matrices, I should just say, right? I get 3 minus 4, 1, and minus 1. So that will be to the power of k then. And then we times this here by this matrix again, but to the power of 1 now. So 3 minus 4, 1, and minus 1 there. Okay. So the left-hand side here is equal to the right-hand side, just using basic rules of indices, right? Now, this matrix here to the power of k, we assume this is true then for n equals k, and we obtain this result here. So I can now replace this then with this matrix here. So what I get then is, so we get 2k plus 1. We then have minus 4k. I've got k in the bottom left corner. And then finally minus 2k plus 1 here. Okay. And we times that by this matrix here. We times it by 3, minus 4, 1, and minus 1. Okay. So what we need to do now then is find the products here of these matrices. So if you're not familiar with, finding the products here of matrices, just go back a couple of chapters here. We have covered this in quite a bit of detail. So rather than showing you the full expansion here, or the full multiplication here with these matrices, I'll just give you what you should get here. So if I don't simplify it, what you'll get here is 6k plus 3. So 6k plus 3 minus 4k. That's my top left element here. You then get minus 8k. So minus 8k minus 4 plus 4k. So what do we get then in the bottom left corner? Well, I get 3k minus 2k plus 1. And then finally here in the bottom right corner, we get minus 4k. Minus 4k there. Plus 2k. And then finally minus 1 here. Okay. So if you find the products here with these matrices, this is what you should get. So if we simplify this here, then what we get here is 2k plus 3. We then get minus 4k minus 4. We then get k plus 1 here. And then finally here we get minus 2k minus 1. Okay. And then we're pretty much done here. All we want to do then is show where the k plus 1s are. So if we do that here, we get two lots of k plus 1 plus 1. And for this element here, we get minus 4 lots of k plus 1. So minus 4 times k plus 1. For the bottom left element here, that would simply be k plus 1, right? We can't do anything with that. So k plus 1 there. And then finally here in the bottom right corner, we get minus 2 lots of k plus 1. And then don't forget here the plus 1. Okay. And there we have it. So in that case, then this is true. So therefore true when n equals k plus 1. Okay. And there we have it. So we've done all the hard work then. So to finish with then, as we do for any proof by induction question, all we need to do here then is give our conclusion. So just as we did for the previous question then, what I'll do here is I'll clear the screen and I will give you the conclusion. So as we mentioned, then we've cleared the screen here, and what I've given you then is the conclusion to our proof by induction. So what do we say here then? Well, if the matrix equation is true for n equals k, then it is shown to be true for n equals k plus 1. And as the matrix equation is true for n equals 1, it is also true for all n that belongs to the set of positive integers here by induction. So again, pretty basic stuff, right? Just writing this conclusion. It is a little bit tedious, I do appreciate that, but it is important to do this conclusion here. You will lose marks if you don't do it. Okay? So there we have it. So that gives us the solution there to the very last question, question 2. And that brings us to the end then of this video here on exam revision for proof by induction.